In this presentation, I will talk about 4 techniques that are used to characterize material and their applications in food science and technology. This presentation will contain a brief introduction regarding the basic principles of these 4 techniques, and then I will explain with more detail each of these 2 spectroscopic techniques and the other analyses that are based on the adsorption process. Moving to the spectroscopic techniques, these are based on the interactions that electromagnetic radiation can have with matter. The interactions are affected by the chemical composition, the physical state, and the structure, meaning the crystallinity or amorphous structure of the atoms and molecules that constitute matter. In the graph, it could be seen that the electromagnetic radiation will have more energy if the wavelength is very short, and on the other side, if the wavelength is very long, they will have low energy. Also, the frequency will be similar to the energy, high frequency, and low energy, low frequency. In this table, it is possible to see the types of interaction that radiation could have with matter and the names of this interaction, such as absorption, transmission, emission, scattering, reflection. And on the image, it could be seen how each of them behaves. So the most commonly used in the spectroscopic techniques are absorption and scattering, but also the others could be useful for several techniques, as those that could be seen in the table. For example, scattering is used in Raman spectroscopy, while absorption is used in atomic absorption, which are the techniques that will be described later. The frequencies and the intensities of the absorbed or transmitted frequency will be influenced by the chemical species that is present in the sample, and the emissions will be unique for each type of chemical product. This will allow the production of this type of graphs that are called spectrum, as the one that is shown in the right side. So the intensity of the signal is placed in the y-axis, while the wavelength is placed in the x-axis. So each wavelength will have a specific emission, and it will be related to the chemical structure of the product that is present on the sample. The physical processes are called absorption, in which case the incident light will cause that the electrons in a lower energy state gain energy and goes to a higher energy state. This is called absorption. Emission is just the opposite. When electrons are in an excited state with higher energy, they will emit light in order to go to a more stable, lower energy state. So these absorptions and emissions are measured and used to construct these graphs. Also, it is important to take into account the so-called Beer's law, which relates the absorbance and the concentration of an absorbing species, and in the determined range, there is a linear relationship between these two parameters. So with equipment that are able to measure the absorbance of a substance, it is also possible to determine the concentration of a given material. It is based on the measurement of the intensity of the initial light source, which then passes by a cell that contains the sample, and some of the light is absorbed there. so the final intensity is lower. So this difference is measured and used to determine, for example, the concentration of a specific chemical in a sample. Moving to the absorption techniques, these are based on the physical processes that are called absorption, and those are related to the addition of atoms, ions, or molecules from a fluid, which could be a gas, a liquid, or a solution of a solid dissolved in a solvent, into the surface of a commonly porous material, solid material. So a film of the absorbate is formed on the surface of the absorbent due to the surface energy. It means that the atoms or molecules of the adsorbent that are on the surface has some availability of bonding requirements since they are not completely surrounded by the other atoms of the material. So they can bond to the adsorbate for this phenomena to be observed. The nature of the bonding depends on the species that are involved. Typically, there's a physical absorption, also called physisorption, in which van der Waals forces are the responsible of the addition of the adsorbent on the surface of the adsorbent. In chemisorption or chemical sorption, covalent bonds are formed between binding sites of the absorbent and the molecules of the adsorbate. And a third type of process is based on the electrostatic attraction that is produced when there are charges on the surface of the adsorbent, and also the adsorbate is formed by ions, either those that are called anions that have negative charge or the cations that have positive charge. This phenomena is commonly described with the use of the graphs that are called isotherms. These are built with experiments in which the amount of the adsorbate that is fixed on the adsorbent due to a pressure of gas or the contact with a liquid with a determined concentration of a solid at constant temperature. That is why they are called isotherms, because the temperature remains constant. So in the graph, it is possible to see how this works. In some cases, the adsorption is very strong, so it corresponds to an irreversible process commonly associated with chemisorption. But regarding physisorption, the absorption could be strongly favorable, linear, or unfavorable, in which case is related to very weak bonds. In any case, the quantity of the absorbed fluid on the surface of the adsorbent is normalized by the mass of the adsorbent, so it could be compared to other materials in order to determine how is the capacity of this absorbent material associated with a specific adsorbate. These techniques could be used to determine the surface area of porous materials, which have micro, meso, and macropores, which are the small, medium size, and big size pores that could be seen in the image. And also, in order to determine the pore size distribution with a graph. This graph will tell how many micropores, mesopores, and macropores are present in a material, and is very useful to characterize, for example, some catalyst. The commonly determined parameters through these techniques are particle sizes, surface areas, and porosity. Regarding Raman spectroscopy, this is a very powerful technique that is focused on the study of molecular vibrations provoked by light scattering. So in order for a vibration to be seen in the Raman spectrum, it is necessary that the polarizability is changed due to the interaction of the emitted light with the vibrating atoms that are part of the sample that is being studied. So this distortion is easier when the bond lengthens and it is harder when the bond shortens, as it could be in the graph. The bonds will have some vibration in which the atoms will become closer and farther away in short times. And these symmetric vibrations will produce intense Raman lines, which will be useful to identify some characteristic functional groups present in the material that is being analyzed. In this graph, we could see how it works. There's a light source which emitted light with a high energy that is called excitation light. So when it interacts with the molecules of the sample, three possibilities are shown. So in the case that the collisions are elastic, the energy will not change, and in that case we have the so-called Rayleigh scattering. But it is also possible that the interactions produce an increase in the energy or a decrease in the energy, in which cases we have these Stokes and anti-Stokes scatterings. The Rayleigh scattering is observed, for example, in the sky when the sunlight interacts with the molecules of oxygen that are present in the atmosphere. So they will become scattered in wavelengths that are close to the visible spectrum in the blue colors. There's why the sky is seen blue by us. But in other cases, if the light comes in a direction that is almost tangent to the Earth's surface, they will be seen as red and white and yellow colors. About 1 photon in a million will scatter with this shift in wavelength. So if there is a shift in a wavelength, there will also be a shift in the energy. So this is what is measured. And it is due to inelastic collisions of the photons with the molecules. In some cases, the photons will be scattered with higher energy. Then we are talking about the Raman anti-Stokes lines. And also, it is possible that the photons are scattered with less energy than the incident light, in which case we are talking about the Raman-Stokes lines. These techniques could use samples with different thickness, so it's not a big concern. Also, there's little interference from the ambient atmosphere. So, for example, there's no need of high vacuum or a purge gas. Also, glass and plastic materials have weak Raman signals, so the samples could be measured inside the glass or plastic packaging. Also, aqueous samples could be measured directly. They don't need to be dried. And each compound will give a specific spectra with a characteristic intensity that is proportional to the amount of this material that is present on the sample. That is why this is a qualitative and a quantitative technique. There's a representation of the components of the equipment that are used for this technique. There's a laser that is emitted through mirrors. It is directed to the microscope objective, which contains the sample, and the scattering will go back and go through a filter to a monochromator, and then will be directed to the detector. Commonly, Raman spectrum is complemented by infrared spectrum because some molecules emit one of these types of spectrums and not the other, or it could be both. So it's easier to identify some materials with the combination of these two techniques. Regarding the applications, the Raman spectroscopy is used for the characterization of bottle materials, for remote sensing, microscopic analysis, mainly for chemical imaging. This means that different types of materials, including organics and polymers, could be characterized through these techniques. It is able to differentiate polymorphs, isomers, and other chemically similar forms, which is very useful because, for example, there are some molecules in which one isomer has a sweet taste, but the other isomer has a bitter taste. So in foods, it will be useful in order to allow only one of them to be present in the product. It could also be used for detecting food adulterants, food additives, to determine the basic components of foods, meaning the carbohydrates, proteins, and lipids. It's also useful to determine the presence of microorganisms or viruses, and also for detecting other risks such as toxins. On the right side, we could see how spectrum will look, in which, depending on the wave number, these peaks could be related to different functional groups, and these could also be related to different type of substances. Moving to atomic absorption spectrometry, represented with the letters AAS. This technique is based on the absorption of discrete wavelengths of light by free atoms that are in gas phase and in a ground state energy. So the samples are transformed into atoms thanks to the use of high temperatures. Then these atoms will interact with the incident energy, moving from a ground state of low energy to states of higher energy, which are called excited states. This absorption will then be measured, and it's also possible to measure the emission. But it is important to say that only those elements that are metals in the periodic table are able to absorb this type of energy, and in consequence be determined through these techniques. The non-metal elements are not identified through this technique. Very, very low concentrations in the order of ppbs and ppms could be determined through this technique, but it has been reported that lower concentrations, included parts per trillion levels, could also be determined. It varies on the sample. It is not necessary to separate the analyte from the rest of the matrix, and the analyte will be identified quantitatively, but it won't be possible to speciate it. it means that it will not be possible to know in which chemical form it is, only to know how much of a specific element is present on a sample. And most equipments work with one element at the time, because it is necessary to vary the wavelength of the light source each time the measurement occurs. There's a explanation of the systems of AAS, in which the sample is moved to a chopper and then put in the atomizer, which produces atoms of this one, of the material. Then the light source will get in contact with these atoms, then goes to the monochromator, to the recorder and amplifier, and finally the readout device. In modern equipment, there are different types of atomizers, including flames and some other heating elements. What samples have been studied in this technique? For example, urine, in studies that are related to the detection of drugs, petroleum products, and food matrices such as wine, fruit juice, and also water. Solid samples can also be studied, including animal tissues, plant materials, different types of food, and polymers, all of which are relevant in the food industry. In all cases, the results will look similar to the one on the graph on the right. Each peak, depending on the wavelength, will correspond to a specific element. For example, in the graph, the green peak corresponds to iron. So it is possible to determine, for example, if foods have the amount of micronutrients that is desired, or if they contain, for example, heavy metals, will be a risk for the health of the consumers. Moving to the absorption techniques, the one that is called Brunauer-Emmett-Teller analysis and is represented by the letters BET. It's based on the absorption of gas molecules on a solid surface, and then the measurement of the specific surface area of the materials. So since the phenomena is absorption, there could be formed, multi-layers could be formed. So it is important that the gas do not react with the absorbent. That's why normally nitrogen is used as the probing gas. In those cases, the experiments are conducted at 70 Kelvin, which is the boiling temperature of nitrogen, but other gases could also be used. Regarding the chemical parameters, BT is an extension of the Langmuir model, which has all of these assumptions. For example, that infinite layers of the gas are absorbed on the material, on the surface of the material. The interactions are only with the adjacent layers. The Langmuir theory is applied to each of the layers. The enthalpy of absorption of the first layer is constant and greater than the one in the second, and this is greater to the one in the third layer, and so on. Also, the enthalpy of absorption of the second layer is equal to the liquefaction enthalpy, and this applies also to the next layers. Then this data is used to create a graph, and then the regression is used to find a linearized BET equation, which is used to transform all of the data into the BET plot. Then the monolayer volume could be determined, which means that it can be known how much of the gas is absorbed on the material, and then this data could be transformed to the total specific surface area of the material, which will be represented in square meters over gram, which means that is a characterization of how porous this material is. There are several stages in the process. First, it is necessary to degas and evacuate all of the gas that could be present in the material. And then the probe gas, which is commonly nitrogen, is put in contact with the material, and the absorption is determined. It is also possible to determine the desorption of the gas, in which case the porous volume, the volume of the pores could be determined. The equations for fitting the water absorption isotherms in foods are very important for food preservation by dehydration, because it is known that when foods are very dry, they will last longer, but it's important that they do not absorb water, because they will have more water activity, and this will produce the growth of microorganisms that will put a hazard on the consumer. Also, other parameters will be interesting to determine, for example, the shelf life of a dry product, the equilibrium conditions after mixing products that have different water activities, and so on. Also, the isotherm equation that is produced through this technique will be useful for evaluating the thermodynamic functions of water solved in foods. And lastly, the Barrett-Joyner-Allenda analysis, or BJH, similar to the one that was previously explained, in the sense that is used to determine the pore area and the specific pore volume through absorption and desorption techniques. In this case, the pore size distribution will be independent of the external area, thanks to the particles size of the sample. This technique, or this analysis, applies only to mesopores and small macropores size ranges, which goes from a few nanometers to around 300 nanopores, as it could be in the image. The modified Kelvin equation is used to relate the partial pressure that is applied through the gas to the material with the amount of the absorbate that is removed from the pores of the material when the relative pressure is decreased. It means that first, all the pores are filled with the probe gas, and then the desorption processes will take place, and this volume will be measured. So this technique will allow to determine the pore diameter and the pore condensation pressure, which will be used to determine other characteristics of the materials. At the beginning, the nitrogen pressure is slowly increased while the absorbed volume is measured. Then it is known that a multi-layer absorption will take place. Then capillary condensation occurs thanks to the high pressures, so that all the pores are filled with liquid nitrogen. At the end, the pressure will be reduced, and then the absorption equilibrium will be measured. The curves of absorption may not coincide in all of their length. This is called the hysteresis. In mesopores, which size goes from 2 to 15 nanometers. The pressure where the condensation takes place is dependent on the pore diameter. And the pore size distribution will be calculated from the desorption isotherm because it comes from the volume that is filled with nitrogen in the pores. The applications in food science and technology are related to the design of separation or purification processes, since porous materials are used in these processes, also for the characterization of adsorbents and other materials, including advanced and nanoscale materials, and also for heterogeneous catalysts. For example, in the graph, it's possible to see the reactor for the hydrogenation of vegetable oil in order to produce margarine. In this case, a catalyst, heterogeneous catalyst is commonly used. And nowadays, it's very important that these catalysts allow to work in low temperatures in order to avoid the formation of trans fats. As final remarks, these techniques are used to characterize foods and also materials that are used in food industry for the production of products of interest. The spectroscopic techniques allow the identification of specific components in which in some cases they are desired, for example, micronutrients, but in other cases they are undesired, such as heavy metals. While the absorption techniques will allow the determination of the surface area and the pore size distribution of porous solids.